Thank you, Elena. Hello, everyone. So today I'll try to give a brief on the source apportionment of oxidative potential, and I'll try to summarize what we know so far. I guess that this presentation can be a good introduction to Zoran's presentation. He will talk more about the measurements and how we are actually estimating the oxidative potential. I will try to cover what oxidative potential really means and how important it is that we consider it more seriously in the future. We know that mass concentration of particles has been a common approach that was used to correlate the atmospheric particulate matter and its effects on human health. And initially, we were monitoring total suspended particles in PM10. Later, we started monitoring fine particles with diameter smaller than 2.5 microns, and then ultrafine particles. The definition is, I guess, still those ones that are smaller than 100 nanometers. And specifically, ultrafine particles started gaining attention for its ability to penetrate deeper in the respiratory system and traveling to other organs. So you already know, I'll just mention a few things that PM2.5 has been associated with preterm births, with cardiovascular diseases, with lung diseases, with asthma, and many other conditions. And epidemiological studies done so far are generally used to evaluate the human effects of atmospheric particles. In all these studies, PM2.5 has been used as a metric, as a dose of particles, as a measure of particulate matter that we, let's say, inhale or digest. And although particle mass concentration is currently used as an exposure indicator, it may underestimate the overall impact of particulate matter, since it does not consider different sizes, compositions, and toxicological effects of its components, and as well as their interactions with other pollutants. So the negative health effects posed by the particles cannot be explained by a single parameter, such as mass concentration, and thus significant empirical uncertainty in the results obtained from epidemiological studies has been observed. So it is possible, for example, that a specific major chemical component that is a large contributor in terms of mass has a low or very low toxicological activity, consequently inducing moderate or no negative effects on human health. So if you have that mass and you see negative health effects, you may think that that concentration of particles is not dangerous for us. However, if you have a low particle mass, but if in that particle mass you have minority or trace chemical components that have very high toxicological activity, then it won't be captured just by mass. And in this sense, we can say that the PM mass concentration, I wouldn't say a poor metric, I wrote here a poor metric, but let's say it's not the best, the most holistic measure for explaining the mechanisms by which particle exposure can induce deterioration in human health. And this limitation that we have, that is posed by particle mass, can be overcome by identifying the possible relationship between PM toxicity and its specific physical and chemical properties. So during the last few years, I would say during the last 15 years, when oxidative potential research has started, but in the last few years we saw very interesting developments in the field. This complex and variable composition of particulate matter has been widely studied, and several PM properties have been identified as important in the determination of its potential health and environmental effects, but they are not entirely conclusive. So we need to discover why. So here I'll try to discuss more, where does the complexity come from? So we have many sources, and all of these sources will give us different chemical composition and different size. So they vary greatly depending on meteorological factors, emission sources, transformation reactions in the atmosphere, and aging as a consequence. And as you can see here, so we have PM emission source, and then we have these multiple reactions that are happening in the atmosphere. That is mainly oxidation by OH radicals and peroxy and hydroxy radicals, which are transforming many species that are prone to oxidation. We also have quinones, PAHs, alcohols, aldehydes, metals. All of them are having high toxicity. So PM contains biological materials such as pollen, spores, viruses, bacteria. It contains organic compounds, especially combustion-generated organic aerosols and biogenic aerosols. It contains inorganic ions, crustal materials, elemental carbon, and metals. Here, under elemental carbon, we have different types of elemental carbon. We won't talk about it. We have black carbon, brown carbon, etc. So these components, either alone or as a part of a mixture, can induce negative health effects on human health. Now, when we have these different components, they together they can react, or one can act as an adjuvant to the toxicity of another. So they can actually increase the overall toxicity significantly. So you can see also here, so these are, this is how our metabolism reacts to the introduction of particles that actually manage to penetrate. I won't go into this, but you can just see that we will have superoxide dismutase that is going to make peroxy radicals and then hydroxy radicals, and then we have whole cascade of reactions here that is causing a free radical chain of our key molecules, such as our proteins or DNA or lipids, and this is later leading to oxidative stress. Now, I will just mention like what different chemical components are doing. For example, salicidions, they have been associated with an increase in morbidity and mortality rates due to their acidic properties or their interaction with other components. For example, sometimes if you have that acidic conditions, they can increase bioavailability of other metals or catalyzing organic reactions. Also, when we talk about organics, it's very widely well known that exposure to polycyclic aromatic hydrocarbons has been associated with lung, skin, bladder cancer, in addition to endocrinal and immune diseases. We have elemental carbon then, that has been associated with hospital admissions that are related to cardiovascular diseases, while organic carbon has been mainly associated with respiratory diseases. So we know that occupational exposure studies and very extensive studies on the exposure to cigarette smoke highlighted that high concentrations of cadmium, for example, are positively correlated with lung and skin cancer. Also, risk of breast cancer due to exposure to transition metals was evaluated through these huge studies that had almost 51,000 participants, and it was found that these transition metals, so cadmium and lead, were associated with a high risk of breast cancer. Additionally, chemical, as I mentioned in the previous slide, chemical components and physical properties, they may have antagonistic or synergistic effect that must be evaluated. It depends on the specific mixture, and this is why it's very important to understand where the toxicity is really coming from. The evaluation of the effects of atmospheric PM on human health then needs to be addressed carefully. In this slide here, I wanted to show you, it's a very complex slide. I won't go into details. I believe Zoran is going to talk more about this. But firstly, I wanted to show you that particles are growing, and as they are growing, and as they are growing in the atmosphere, they are changing their chemical composition. And you can see here, so we have precursors, then precursors are exposed to different oxidants, then we have particles growing, being more oxidized by ROSs, which is reactive oxygen species. I will introduce them soon. Or RNSs, which are reactive nitrogen species. Then we get these nanoparticles that are growing by condensation and by some less oxidized molecules. And then we have here submicron particles. You can see here that nanoparticles, they can be very toxic. They have a lot of ketones, aldehydes, as you can see, amino groups, carboxylic groups, OH groups on their surface. In Zoran's group, we did a lot of studies on the morphology of particles and these chemical bonds on the surface of particles, and we were trying to relate this composition of particles to their sources. So we know that the organic component of primary particles tends to be less oxidized, as you can see here, like you will mainly have soot. And then in organics, there can contain unique compounds that serve as tracers of specific sources. And this is how we do source apportionment. Then when particles stay for a longer time in the air, we have secondary organic aerosols, and they are even more complex. And this is what happens here. So we have a lot of different oxygenated species, and we have a lot of nitrogen and sulfur containing organics or heterocyclic amines that are highly toxic. My research so far has shown that the most toxic component of particles is actually coming from the oxygenated organic fraction. Now, we have a growing number of measurements and studies that were dealing with secondary organic aerosols, and they showed that highly oxidized molecules with high molecular weight are relatively more important in smaller particles than in bigger particles, because growth to larger diameters involves less oxidized lower molecular species, as we said here. Now, what is oxidative potential? Whatever like PM negative health effect has been attributed to the property of particle to oxidize the surrounding tissues. We have a current research hypothesis that many of the adverse health effects are derived from oxidative stress in biological systems that is caused by the deposition of particles into lungs. So this is called oxidative stress paradigm. And what it means is that if you inhale a lot of particles that are having reactive oxygen species on them, then we don't have enough antioxidants to fight them. And once this balance is ruined, once we have more ROSs than antioxidants available, then we have oxidative stress. When we talk, what is ROS? ROS is a collective term that is describing reactive oxygen radicals, and this is a large family. You have hydroxyl, peroxyl, alkoxyl, oxygen-derived species, ozone, singlet oxygen, peroxide, etc. And when we talk about ROSs, we have two types of ROSs. So we have exogenous ROS. This is ROS that is contained on a particle, and this is ROS is basically going to be carried by the particle into the lung. And the second mechanism is that when a particle hits our lung, it can create ROSs, and this is endogenous ROS. So oxidative stress represents a relative mechanism of toxicity derived from particles, and the oxidative potential, or OP measurement in particles, can be a first step in the elucidation of the subsequent downstream processes. So this is a measure of that oxidative stress. However, the relatively complex measurement processes in biological systems make it very difficult for us to monitor the ROS parameter in the environment. Zoran will talk more about it. It's very challenging. Here, I'll just mention that to monitor oxidative potential, we are employing mainly cell-free tests because they are cheap, they are easy, they are not labor intensive. The problem with oxidative potential measurements is that we have many cell-free assays that we are using, and every assay is detecting specific species. So we currently don't have an assay that will detect every possible ROS that is available on particle. And this is why we propose that instead of using only one, we try to use 2 or 3 in parallel so that we can cover a wider range of chemical components on particles that are detectable by these probes. So we have these cell-free assays like DTP and ascorbic acid that can be used in cells as well, and they are direct measure of oxidative potential. And then we have some probes that our group at QUT was using. We were measuring particle bound ROS, and probes are DCFH and nitroxide. They use fluorescent-based techniques to measure concentration of specific ROS. So based on the amount of fluorescence, we know how much ROS we have inside. And unfortunately, these methods usually reveal a different response to the chemical constituents of PM, so that is one of the limitations we have. So how do we report oxidative potential? So we estimated using the methods that I've just described, and we express it as the oxidative potential that is normalized to the volume of air that is containing certain concentration of PM, or as the OP normalized to the mass of particles that is representing the intrinsic OP of the PM. Sample collection of ambient PM has been done by different methods. Zoran is going to talk more about it. I'll just mention them. So we have high and low volume samplers. We have ACES, a particle into liquid sampler, particle into liquid quencher, which was designed by Zoran and me and our student. We have samplers that are based on the condensation of particles, such as MAUDI, if we want size segregated samples to analyze further. Automatization and online measurements have been a growing area of study as they have the potential to significantly reduce the analysis time, reduce materials, and they also help to obtain data with better time resolution and more accurate chemical composition. Size of particles matters. So here we have, you can see different sizes of particles and you can see where they end up. So these brown ones, these are these large particles, 7 to 10 microns. They will mainly end up in nasal cavity and oral cavity. Then we have 5 to 7 microns, they will mainly be in trachea and bronchus. 3.5 is going to be in bronchus, sorry. And then we have 2 to 3 microns. They are going to be here in secondary bronchus and terminal bronchioles. And then we have PM1 and these nanoparticles, they are going to mainly be in alveoles. So this is only these small particles can penetrate to alveoli directly. So compared with larger particles, smaller particles or ultrafine fraction have a much higher deposition efficiency, as well as a higher penetration in these lower parts of the respiratory tract. And based on the clinical studies, the abundance of natural antioxidants in lung lining fluid decreases remarkably as you go down to lower respiratory tract, where smaller particles are prone to deposit. We don't have enough antioxidants there, and this is why the damage from ultrafines is very serious. The particle size dependence of mass normalized ROS activity is exhibiting lowest intrinsic ROS activities in the coarse mode. Because, you know, it's the largest mass. So when you divide the largest mass, you get the lowest OP values. Why smaller particles are considered more toxic? It is mainly driven by the fact that higher water solubility, as well as higher water soluble mass fraction of redox active metals. And this trend could also be, at least in part, attributed to the higher abundance of water-soluble organic species, mainly originating from SOA. So It should be noted that in reality, the oxidative potential of smaller particles relative to larger particles may be even greater than what is measured by any assay.
Svetlana, please make sure you are over time.
Yeah. Sorry. So we have a source apportionment of estimated OP values that is resulting from different field campaigns, has shown differences among assays and site studies, along with high temporal and spatial variability in each site. So studies conducted to date have examined the toxicity of PM collected at urban areas of interest, including locations impacted by nearby roads, airports, harbors, power plants, refineries. And here, I won't go through every one of them, but you can see that mainly traffic emissions, they're always approximately around 50 to 40% of OP is caused by vehicles, which is followed by SOA and biomass burning. Again, similar conclusion from Beijing. So we have vehicle emissions, secondary sulfates, and coal combustion and dust. In France, it was found that the primary road traffic and biomass burning are the main absolute OP contributors. In Bangkok, we saw shipping emissions and a huge amount of biomass burning as secondary sulfates. Here, also contribution of metals and aromatic substances to OP, it is very established. In these large studies, the newest study in Europe, OP is associated mostly with anthropogenic sources, fine mode secondary organics, and biomass burning. You can see this pattern is repeating. And Campbell et al., so this is Cambridge group, they have basically found that metal-related factor, marine vessels, vehicle emissions, and biomass burning has a predominant contribution to OP. So I will skip this one because it mainly has very similar conclusions. So I'll finish with the fact that we use land use regression models to explain the spatial distribution and association of the estimated OP with variables. The variables we need to take into account are traffic count, traffic flow, population density, tree coverage, CO and NOx emissions, distance to railroads, and then commercial land use of parks, residential, industrial areas, distance to highways, restaurants, airports, buildings, and harbors, as well as regional background. So conclusion is that previous knowledge on the relative contribution and relevance of local emission sources can be very helpful in building up the related OP values responsible for the generation of ROS. The results obtained for a sampling area must not be extrapolated to others. And also OP estimations using different emission sources and size fractions are needed to help understand which PM sources could represent a significant health hazard. And this was the point. These are the questions that are remain to be answered. I will finish with this slide. So you can say that we want to know how PM really damages human health, which concentration is risk-free, is the damage caused by the physical or chemical properties or their interactions. We want to know which chemical constituents are the most dangerous. Is there a method to measure how dangerous they are, and what would be the best metric other than PM mass concentration? So thank you for your attention. I will leave this slide on. So this is summarizing basically this leapfrogging to oxidative potential between sources and risk management. Thank you for your attention, and I'm welcoming your questions. Sorry that I went over time.